Good morning, everyone. My name is Eugene Park, faculty member from the graphic design program at the University of Minnesota Twin Cities. And I'm presenting on behalf of my collaborators on this joint endeavor that we are calling Drawing Water, which is a multidisciplinary project to represent water performance. This is a collaborative pursuit funded through an internal grant by our university that specifically supports the different design fields working together. So in addition to myself, I was joined by Jessica Rossi Mastracci from Landscape Architecture and Matthew Tierney from Architecture. And our grant was used to fund 3 graduate research assistants, each representing the co-PI's fields. So the problem that we wanted to solve is to improve the ways in which we can visualize water and all of its states and qualities that can be useful for architects, designers, and engineers when planning for specific climate scenarios on a given site. Most representations of water, notably through consumer-centric maps, represent water through static formats largely based on their print counterparts. Even for more technical diagrams, such as hydrographs, they are limited to conveying a water's flow as an aggregate mass without the complexities that come with water flowing into different sources and mediums. There are also plumber riser diagrams, which are technical drawings that illustrates a building's water supply and waste lines, but they only offered a limited view of water flows within a specified infrastructure. So what we wanted to explore is how all of these representations of water, each offering a specific vantage point, can be brought together into a more expansive representation. And to achieve this, we will need to explore different combinations of water representation techniques from architecture, landscape architecture, cartography, engineering, and graphic design to visualize hybrid solutions that can represent a water's dynamics character. To explore our representation methods, we selected Ralph Rapson Hall at the University of Minnesota as our site of study, primarily due to its proximity and our collective familiarity with its architecture and landscape. For the purposes of this project, we decided to examine this location from 3 different scales, the smallest of which is the site itself. Then there is the campus scale, and then finally the largest of which is the watershed, which is an area in which water from various sources gets channeled into an outflow point, which happens to be the Mississippi River for our specific site. So we began the project with assigning our graduate students to audit current visualization conventions in which water systems can be visualized. They were also asked to sketch out different ways in which some of these graphics can be combined or adjusted to create new hybridized graphics. Since this is a collaboration between multiple design disciplines, it was important for us to establish a shared language as well as an understanding of what visualization techniques are available for the scope of this project. So we work with our assistants to review all of their drawings and to create a matrix that contains various methods and their use cases at specific scales. Into the next phase of the project, we designed an interactive web-based tool that can be actually used by architects, designers, and engineers to see how water affects a given site. We wanted the user experience behind this tool to center around 2 kinds of visualization. The first of which is a set of maps that showed the land use and water flows on a given space. And then the second visualization is a Sankey diagram that gives a more expansive view of the water flows on a given location. So putting everything together, we created a Figma prototype where all of these controls and variables can be used to understand how water flow and usage can have an impact on a site. Flanking both sides of the visualizations are user controls that can be used to specify the site through its GPS coordinates, and users can also set necessary conditions to simulate water-related scenarios, such as through soil levels, precipitation events, water storage, evapotranspiration, and infiltration of water into the surrounding landscape. So the point is to allow an architect or a designer or an engineer to input these values to simulate the site and its surrounding conditions to see how water flows will change depending on any adjustments that are made. So in this current view, all of the controls are set to the existing site conditions as the control scenario. and users can adjust the controls to see how conditions can change. For instance, when we focus on evapotranspiration, we want to think about how to maximize the use of green areas. Or we can focus on infiltration, which is creating areas to direct runoff water to stormwater retention and detention basins. Or we can try to maximize water storage by collecting and storing all the runoff water in order to use for irrigation. Now, this prototype is still a work in progress, and more development will be needed to make it feature complete. So the next steps is to complete the prototype, to visualize the campus and watershed scales, conduct user testing, integrate live data connections beyond a Figma prototype, and then also to improve the readability of the visualizations. So in conclusion, the task of representing water in all of its complexities requires the collective expertise from multiple disciplines, from design to engineering. And fulfilling this task will require a shared language around nature amongst these multidisciplinary teams. As climate change continues to affect the intensity of water patterns and threaten habitats, it will become increasingly important for the designers involved in this to be equipped with this shared language of understanding that will allow us to develop more sophisticated and multifaceted solutions that will help increase climate resiliency. And thank you very much.